Have you ever noticed how a fresh piece of toast, piping hot from the toaster, just quickly loses all its crunch and heat if you leave it out?
Oh, absolutely. That soggy toast problem.
Exactly. And that whole relentless march toward, room temperature, it's happening everywhere, all the time. But what you might not realize is that this simple physical thing is governed by one of the most powerful and really elegant mathematical structures ever conceived.
That's it. Today, we're doing a deep dive into the heat equation. Joseph Fourier formulated it back in 1822.
And its mission, so to speak, was just to model heat.
It was. But what we're going to show you is that this equation is actually a kind of mathematical blueprint for diffusion and smoothing, and equilibrium across fields that seem totally unrelated.
Okay, so let's unpack that. We're talking about a partial differential equation, a PDE.
Right. And for anyone who's a bit rusty, that just means an equation that involves changes based on more than one variable. In this case, temperature changing over both space and time.
So at its core, the heat equation is saying that the rate of change of temperature over time
Is proportional to its spatial curvature. We call it the Laplacian. The notation can look a little intense, but the concept is just beautifully simple.
Let me see if I can translate that. So the material heats up or cools down depending on whether the area right around it is, on average, hotter or colder.
Exactly. The Laplacian is just measuring how bumpy the temperature map is.
So where you have the biggest bump, where hot and cold extremes are right next to each other, that's where the change happens fastest.
It's the second law of thermodynamics in mathematical form. Heat flows from hot to cold, always smoothing things out until you reach a perfect equilibrium.
And that smoothing process,
Yeah.
it's not universal, right? My tea cools way faster with a metal spoon in it than a wooden one.
Absolutely, and the math has to account for that. That speed is governed by a constant, alpha. We call it thermal diffusivity.
And that combines a few things, doesn't it?
It does. It combines the material's ability to conduct heat with its ability to store it, so it's specific heat and density. A material like metal has high thermal diffusivity, so the heat, it just smooths out lightning fast.
Okay, so this idea of smoothing is what makes it so flexible.
It's the unifying idea, because the equation can model any diffusive process. Think of a plume of smoke dissipating or a drop of dye spreading in water. The applications just explode far beyond temperature.
This is where it gets really surprising. I was reading that it's used to solve fundamental problems in, of all things, geometry.
Yes, in Riemannian geometry, that same smoothing principle helps us understand the structure of really complex spaces. The solutions there are called heat kernels.
Heat kernels, what are they telling us?
They show how heat would spread from a single point across some uneven, maybe curved surface. Understanding those kernels gave mathematicians critical insights that were, well, essential for the proof of the Poincare conjecture.
So the way heat moves can actually tell us about the shape of the space it's moving through. That's incredible.
It is.
But I have to ask, physics and geometry, I can sort of see the link, but finance. How can an equation that predicts water cooling also predict a stock price? I mean, markets are driven by human choice, not physics.
That's the absolute genius of the Black-Scholes model. They realized the random, unpredictable movement of stock prices, kind of Brownian motion, could be modeled as a form of diffusion.
So they treated price volatility like heat flow.
Exactly. And suddenly, all the techniques Fourier developed for temperature could be used to solve financial problems.
We even see this in things like image processing, right? Using the heat equation to smooth out noise in a digital image, but keeping the important sharp edges.
Yes, it's key for complex recognition systems. And that kind of modeling is, it's computationally very demanding.
It certainly is. Complex mathematical modeling like that requires reliable infrastructure.
Mm-hmm.
Which actually brings us to our sponsor for this deep dive, Embersilk. If you need help uncovering where AI agents could make the most impact for your business, from automation to integration and software development, check out embersilk.com for all your AI needs.
So we've seen how this one elegant structure, the heat equation, it bridges the gap from something mundane like a cooling cup of coffee.
Monumental, like the behavior of subatomic particles, pricing financial derivatives, and even the fundamental structure of space itself.
The journey from Fourier looking at a hot metal rod to solving some of geometry's toughest problems, it really shows how deeply unified the universe is by these mathematical structures.
It really illustrates that the tools we build to understand the physical world often end up unlocking these profound new realities we never expected.
It's a truly inspiring thought, the interconnectedness of it all.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.